right, good morning. How's everybody doing?
Good, how are you?
I'm good too, thanks.
Still confused about the last concept. I'm sorry, Nick.
Confused about the what? Oh.
The empty set.
Mm. Yeah, we can talk about empty sets. It is a strange concept. In some ways, in some ways, it's very straightforward, but it's the things that are seemingly so straightforward that are often the most confusing. Basic idea of the empty set, right? It's just a set that contains no elements. So are you asking about the empty set being a subset of another set?
It was whatever, it was like a zero with a line through it.
Mm-hmm.
Another set. I don't know, like
So we had some discussion about how the empty set is a subset of any set, and I think that was probably the weirdest thing we talked about. So that the definition says, you know, A is a subset of B if and only if any A contained in A, for any A contained in A is contained in B. So to say that this is a subset of that means that any element in here is contained in there. Well, suppose that A is the empty set. So the empty set is a subset of B if and only if for any element in the empty set, the element is also contained in B. Well, the only way that this can be false is if there is some element in here that's not in B. Right? And that is never the case. There is no element in here that's not also contained in B. Because there are no elements in here. So it's kind of true in a trivial reductionist sense of truth, right? If this is not a subset, it means you can find something over here that's not contained in there. Well, you can't. You cannot find anything that's in this set that's not in that set. So this is a subset of that. And if that's logically not quite crystal clear, that's a good thing. Right? That means that you're thinking about this beyond sort of the intuitive, seemingly obvious part. But from the definition of this, right, any element we pick in here has to be in B, right? Well, that's absolutely true. If we could pick an element in here, it would have to be in B, but there are no elements to pick from here. So this is, in sort of a vacuous sense, a subset of B. We're going to find even stranger looking versions of this type of logic when we talk about conditional statements. And that may actually help with making more sense out of this. Does that make any sense?
sure.
Let's see, but we can't find nothingness in set B. This is true. So think of this as arguing in a court of law. Suppose someone comes up to you and says, you know, claim the empty set is not a subset of B. Okay. So you ask this person what X is contained in phi such that X is not contained in B. In other words, if someone comes up to you and claims that the empty set is not a subset of B, you can turn around to them and say, okay, show me some element X that's contained in here and not contained in there. If you can show me that, I'll agree this is not a subset of that. And challenge the person making the statement to show you at least one element contained in here that's not contained in there. They cannot do that. They cannot come up with an element that's in here over there. Is there a donkey in here? No. Is there the number 2 in here? No. They can't find you any element in here, let alone an element that's in here but not in B. So since you will fail to find such an X, you cannot say that the empty set is not a subset of B. And so you're forced to conclude that it is a subset of B, whatever B is. Now B does not contain the empty set. It contains every element contained in the empty set. What we're not saying is this, right? The empty set's not an element of B. It could be, but it doesn't have to be. Right? But that being an element of this set is different from being a subset. Being a subset simply means whatever you find in here, you also have to find in there. And since we can't find anything in here, this is sort of, you know, in the strongest default sense, a subset of that.
If you were to think about it in coding terms, can one make the claim and be correct in saying that empty set is a child of set B?
Is a what?
A child, like B is a parent and the empty one is a child, or vice versa.
There's cases in programming where we would say something like that, and it would be analogous to this. I'm thinking of trees and nil children.
Yeah.
And if that works for you, that's a good way to think of it. If that doesn't make sense, don't worry about it for now. But yeah, there are analogs there. All right. Other comments, questions? So I want to continue talking about set theory. And I want to look at operations we can do on sets and ways we can build new sets from old sets. And then somewhere before the end of class today, I want to look at the homework. So I posted your first homework assignment, and I'm going to make that due on Monday. And this is assuming we get through what I plan to get through today. We'll look at the homework. We'll talk about what you need to do for the homework. And then, ideally, you're going to work on the homework and get it pretty close to finished by Friday. So that if Friday comes and there's something that you're not sure how to do, you can ask about it in class on Friday. And then we can clear up any final misunderstandings, and then you have the weekend to actually write up and submit the homework. And it'll be due Monday at 12:30. And this is going to be the general scheme I'll try to follow in this and my other courses, for that matter, is after we talk about the homework and after you've got pretty much everything you need to do the homework, I'd like to have one more class during which, you know, after having worked on the homework, you can ask questions about it. Okay? And this goes back to the idea that, you know, my email availability is basically once per day, not on weekends. So if you start looking at the homework Sunday and you're not sure how to do something, you can try to catch me in office hours Monday, right? Or maybe you can get one round of email to me. But really, you know, after we go through it today, you want to at least go through the homework and figure out in your head how you're going to do each of the problems, right? So that if there's a question and you can say, you know, I have no idea how to do this, I don't know what this question even means, or I kind of know what we're supposed to do here, but I can't figure out how I would finish it, right? Then we can talk about it in class on Friday. And I really, really, really want to spend class time talking about homework, right? Or I want our discussions about homework to be during class time so that everybody can hear this and we can all participate. So we'll get there in a little bit. But let's continue talking about set theory. Let me find my notes. My notes have vanished. Here they are. All right, so we were talking about subsets when we finished on Monday. And we just talked about them a little bit more. So subset is a way to compare two sets. We talked about equality of sets, right? So saying that two sets are equal means X is an element of A if and only if X is also an element of B. Saying that A is a subset of B means X is in B if X is in A. So being a subset means that if there's an element X in A, it's got to be contained in B. So everything in here is also contained in there. Saying two sets are equal means that they have exactly the same elements. So anything that's in X in B is also in A, and anything that's in B is also in A. Sorry, and anything that's in A is also in B. So we could show that A is equal to B if and only if A is a subset of B and B is a subset of A. So two sets are equal if each is a subset of the other. And that's exactly the case when two sets are equal. Now, if this is true, but that is not true, then A is not equal to B. A is simply a subset of B. But if you look at the definitions, when we say A is a subset of B, it means if X is in A, then X is in B. And when we also require B to be a subset of A, that means if X is in B, then X is in A. If you put those together, that's saying X is in A if and only if X is in B. That means A is equal to B. So this is a theorem that we could actually prove just by applying the definitions of subset inequality. So it's called a proposition or a lemma. It's a small theorem. But this turns out to be a really useful way to test equality sometimes. In fact, in a lot of mathematics, when you're trying to show that two things are equal, this is exactly how you tackle it. And usually one of these directions is clear and the other one takes all the work. So we have equality and subsets. In a Venn diagram, that's what it looks like if A is a subset of B. It's completely contained inside, which basically means any point that we find in A has got to be in B, which it is because all of A is inside B. A different case would be, here's B, here's A. Well, here's some stuff in A that's not in B. So here A is not a subset of B. Here it is. It's also pretty clear if you think about it that A is a subset of itself. Because to say A is a subset of A means that anything you find in here has got to be in there. Well, since here and there are the same set, right? Anything I find in A is in A, this is guaranteed to be true. So every set has at least one subset, which is itself. And it also has the subset, which is the empty set. So most sets have at least two subsets, the empty set and itself. And you'll sometimes... question?
I'm sorry. Say again what it means when there's a line under each. A underlined is a subset of A underlined.
Oh, I just underlined because I was gesticulating. But you can't see me wildly waving my hands, so I underlined them. It doesn't mean anything. Right, I just underlined them for emphasis. But there is another notation that we will see, which is A subset B with a slash going through that horizontal line. And that means, yeah, A is a subset of B, but it also means A is not the same thing as B. Because we always know that a set is a subset of itself, but it's more interesting when you have different sets where one is a subset of another. And so this is sometimes called a proper subset. Or I would think of it as an interesting subset. So for example, right, this set is a subset of that. We could also say it's a proper subset, because this is not the same set as that. And mostly we're interested in proper subsets. All right, let's talk about the size of a set. So first of all, a finite set is a set with a finite number of elements. So that's a finite set, that's a finite set. My set with the mouse and the pen is a finite set. It's got 2 elements. If it's not a finite set, it's what we call an infinite set. An infinite set contains an infinite number of elements. So, let's talk about that. So what do we mean when we say an infinite number of elements? How big is infinite? It's big.
So big it can't be measured almost.
So it can't be measured in some sense. Here's the way that I think is most useful to think about infinite. It's bigger than any number. Right? The number of elements in an infinite set is larger than any number you might think of. So think of the number a billion. There's more than a billion things in the set. Think of the number 10 skrillion, gazillion, quadrillion, million, billion. There's more than that many elements in the set. Right? So it's not that infinity is a number. It's almost the opposite. Right? It's the idea that the number of elements in the set is bigger than any number you can think of. Think of a number, there's more elements than that. Think of a bigger number, there's more elements than that. That's the real concept of infinity. And yeah, we are definitely going to talk about different infinities. We'll do that on Friday. So an infinite set contains more elements than any number that you can think of, or any number that exists. So an example of an infinite set would be the set of all integers. Because, you know, does this contain only 1,000,000 elements? Well, no, I know it contains the numbers from 1 to 1,000,000, and it also contains 1,000,001, 1,000,002, 1,000,003. So it's got at least 1,000,003 elements to it, which is bigger than 1,000,000. Does it have 1,000,000,000 elements? Well, I can count from 1 to 1,000,001. That's more than 1,000,000,000 elements. And I'm still not done. There's still more stuff in this set. Any number that I think of, I can easily show there's more than that many elements in this set Z. So Z is an infinite set. Alright, so if we're talking about finite sets, so if S is a finite set, then we have the following notation. We write S inside absolute symbol bars, so paravertical bars, and absolute value of S means the number of elements in S. So if this was our set A and this was our set B, we could say the size of A is 3 and the size of B is 5. But there's a fancier word for this. Which is the cardinality of S. Okay, why do we have a fancy word for this? Why don't we just say the number of elements in S? Because if S is a finite set, this means the number of elements in S. But if S is infinite, there is no number that is the number of elements in S. That's the whole point of a finite set. So we can't use this definition for an infinite set. So we use this definition. And we say that S inside vertical bars means the cardinality of the set S. Now for a finite set, cardinality is just size. It's the number of things in it. For infinite sets, this gets really interesting. And this is what we'll play with on Friday. We'll look at the cardinality of infinite sets. But we can't write, vertical bar S equals infinity, because infinity is not a number, right? We can't say, the number of elements is infinity, because it's not an integer, right? It's not a number of things. In fact, the number of things is bigger than any number we can think of. So there's a more general definition of this. So for today, we'll stick with finite sets when we do this, and we'll just say this is the number of elements in the set. But we'll make it much more interesting in a couple of days. All right, so that's cardinality. So let's talk about power sets. So we're just laying down some infrastructure here, right? Infinite sets could be discrete. So the set of integers, those are discrete elements in some sense, but that set is still infinite. So infinite sets could be discrete. All right, so we're laying down some machinery for things we're going to do the rest of the course. These are things that will come back in different forms. So let's talk about power sets. If S is a set, then we write the script P of S, which is the power set. Of S. I'll talk about the homework in a minute, towards the end of the class, because I have to look it up. So P of S is the power set of S, which is the set of all subsets of S. So we know what subsets are, and we can find different subsets of a set. Take all of those subsets of S, throw them into a new set. That set's called the power set of S. So suppose S is a set containing the number 1 and the letter B. So the power set would itself be a set, and the elements of this set are all the subsets of S. So what are some of the subsets of S? Somebody give me a subset. Singleton set containing 1, very good. Singleton set containing B. Set containing 1 and B, good. And the empty set. Any others? Yeah, I got itself 1 and B, which is S. And I think that's it. So the power set contains 4 elements, and each of those elements is itself a set. That's okay, we can have sets inside sets. So suppose T has 3 elements, A, B, C. What are some of the subsets of this? So there's the singleton set A, singleton set B, the set containing A and B, the set containing A and C, set containing B and C. Someone did singleton set C. And there's the set itself, A, B, C. And there's the empty set. So 1, 2, 3, 4, 5, 6, 7, 8 elements in the power set. And I think that's it. And let's be really clear. A is not an element of the power set of T. A is an element of T. It's right there. But if I look in the power set, I don't find the element A. I find 8 sets. I find a set containing A, but a set containing A is different from A. Right? A is an element of this set, but A is not the same as this set. A is not even a set. A is just A, it's just a letter. Let's see, so the power set of S is a subset of S, and S is a subset of the power set of S. The power set is not a subset of S. To say that the power set was a subset of S would mean that anything contained in here had to be contained in here. Well, curly bracket 1 is not an element of S. Right, so this is where the road meets the rubber, right? This notion of sets versus elements, really similar but fundamentally different. So these are different sets. And you'll notice that, you know, in both of our examples, the empty set was an element of the power set. And that's because the empty set is a subset of every set. And also, the power set of S contains S. The power set of T contains T. And you notice up here we had 2 elements and the power set had 4. We have 3 elements, the power set has 8. Anybody want to generalize a rule from that? Yeah, 2 to the number of elements. So we can write a really kind of cool looking formula here, which says if S is finite, the cardinality of the power set of S is equal to 2 raised to the cardinality of S. And this is true. And 10 weeks from now, this will be popping up in your dreams, because we're going to come up against this fact so many different ways over the next 10 weeks. Can you make a power set of a power set? You can make a power set of any set. So let's try this. Let's just have A be the set containing the number 2, so it's a singleton set. So the power set consists of all the subsets of A, which is the empty set and the set containing 2. Well, let me call it the empty set and A. So it's got 2 elements. So the power set of A would be all the subsets of this set containing 2 elements. Well, that's the empty set. It's the set itself. and the two singleton sets, a set containing the empty set and a set containing A. And we feel that that's right because this set had 2 elements, this has 4 elements, which is 2 to the 2. That seems reasonable. So this is a thing. And it's absolutely not equal to the empty set. How do I know that? Because the cardinality of this set is 1. This set contains 1 element, which is this funny Greek letter, which happens to mean the empty set. Whereas the cardinality of the empty set is exactly 0, contains no elements. This contains 1 element, which is phi. If I had 2 empty sets, can you combine them, or do you have to keep them distinct? If I had a set and I was listing empty set as an element of it, I would only list it once. But we will play around with the empty set a bit more and putting it together with stuff. Yeah, really easy to mix up elements and sets. Here's a fun thing to try at home. Start with the empty set, figure out what the power set of that is, then figure out the power set of the power set of the empty set, then figure out the power set of the power set of the power set of the empty set, and see what you come up with. I'm not going to do that in class time, but yeah, similar feeling in the derivation of this, definitely. Alright, so try that at home if you want. It's fun stuff. Let's see, for S equals 1b, you said that the set containing 1 is not an element of S. But 1 is an element of S. Yes, that is correct. Right, so if this is our set S, the set containing 1 is not a member of this, because I only see a 1 and a B. I don't see a set at all in here, right? So yeah, what you wrote in chat's absolutely correct. All right, so we're going to keep making new sets from old sets. So our next derivation is something called a Cartesian product. So if A and B are sets, A cross B is the Cartesian product of A and B, and this is a set. All right, the elements of this set take a little bit of explanation. And so, oh, there's a lot of linear algebra in here, definitely. So we've been talking about sets. A set is an unordered collection of stuff. The counterpose to that is an ordered tuple, or an ordered tuple, is an ordered collection of things. So it's like a set, except the order matters. And since the order matters, we can have repeats of elements. So an ordered tuple, an ordered n tuple, is inside parentheses a collection of elements, which we could call A1, comma, A2, comma, dot, 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 up to AN. If you're taking linear right now, that's really good. This will help with linear, I believe, and linear will help with this. The two subjects really play off each other nicely. So that's fortunate timing. So an ordered n tuple, we just sort of list in parentheses n elements from something, right? The classic example we think of is, coordinates. So you have like an xy plane, and here's some point with coordinates 2, 4, 6. Right? This thing that we write, well, that's an ordered 3-tuple. It's a collection of 3 things, and the order in which these things appear is definitely important. And, we could have a point right here whose coordinates were 1, 1, 1. Well, 1, 1, 1 is another ordered 3-tuple. All right, so if we know what an ordered n-tuple is, we can define the Cartesian product of two sets A and B. And it's the set of all A comma B such that A is contained in set A and B is contained in set B. So let's do an example. So suppose A is the set 1, comma 2, and B is a set containing the elements x, y, and z. And this is different from the cross product in physics. It's just a similar notation.
Oh, goodness.
Cross products are funky, right? All right, so if this is the set A and this is the set B, a Cartesian product of A and B will be a set, and the elements of that set are ordered tuples, 2 tuples, where the first element comes from A and the second element comes from B. And so we basically go through and we exhaustively find all the possible elements, all the possible 2 tuples where the first element comes from A and the second element comes from B. So I'm just going to pick on the first element of A, and I could put a 1 with X, I could put a 1 with Y, I could put a 1 with Z. I could take the second element from A and have a 2 with X. I could have a 2 with Y, or I could have a 2 with Z. And those are all the tuples we can get from A and B. And so that's what the Cartesian product of A with B looks like. And just like the cross product from physics, this is not commutative. So if I did the Cartesian product of B with A, this is the set of tuples where the first element comes from B and the second element comes from A. And this set is completely different from this one. In fact, there's no overlap between these two sets, because the tuple 1 comma x is not found anywhere in here, right? Because 1 comma x, x comma 1 are not the same because the order matters in these tuples. And y comma 2 is not found anywhere in here. So these are completely different sets. And in general, A cross B will not be the same as B cross A. But here's something cool we can say. Assuming that these are finite sets, How many things do we find in the Cartesian product of A with B? There's a nice formula for this. The amounts multiplied. Right, it's the number of things in A times the number of things in B. Because for each thing here, we can find, that many tuples where the first element comes from, that element in A, and the second element is any of the elements in B. We'll come back to this when we talk about counting. This will tie into something called the product rule. So that's a nice relationship. And the last comment I'll make here is we can do this for more than two sets. And there's some ambiguity you'll find in what this actually means. If we think of this as this, right? This would be a set of tuples where the first element came from A and the second element came from this, which means this would be a tuple containing elements from B and C. But it's more common when you write something like A cross B cross C that we would mean by this a set of three tuples, right? The set of all A, B, C, such that A is in A, B is in B, C is in C. But technically speaking, that's not the same thing as this, which is also not the same thing as this. But it's usually clear from context what we mean. And the more common situation, almost always the situation is going to be when we write this, what we mean is a set of three tuples. This is why it's fun that this is not a math course, right? Because we don't need the absolute blinding rigor that we would have in a pure mathematical treatment of this stuff. Alright, so on to set operations. So making new sets out of old sets. This is what we do most of this course, is we make new stuff from old stuff. When we study propositions, we'll be spending our time making new propositions from old propositions. Here we're dealing with sets, so we're going to make new sets out of old sets. So, let me just make a general. Let A, B, C be sets in some universe U. So A, B, and C are just general sets, so I don't have to keep saying let A be a set, let B be a set. The union of two sets A and B is written like this. It's A with a cup, a U, right? Sometimes called a cup. So the union A union B equals the set of all elements X such that X is in A or X is in B. So take the stuff from A and B, throw them together. All right, examples. So if I take the set 1, 2 and I union it with the set 3, 4, I get this. If I take the set 1, 2 and I union it with the set 2, 3, I get this. I absolutely do not want to list the 2 twice, because we don't do that when we're writing down the members of a set. We're simply listing the members. So the members of this union are 1, 2, and 3. In a Venn diagram, if this is the set A and this is the set B, that's the union. It's all the stuff taken together. The intersection, A intersect B, is the set of all elements X such that X is in A and X is in B. So it's the things that are in both A and B. It's the overlap. So 1, 2, 3 intersected with 1, 3, 5. Well, I need to find anything in the universe that's contained in both of these sets. So while I could look at the number 1, that's contained in both sets. That's good. I could look at the number 2. Well, that's not contained here, so it's not in the intersection. I could look at the number 3. That's contained in both sets. And any other thing that I pick from the universe is not going to be contained in here, because this only contains 1, 2, and 3. And I already analyzed those 3. So the intersection of these two sets is just 1, 3. I could have started from here also. I could have looked at the 1, said that's in both sets. Looked at 3, that's in both sets. 5, that's not in the intersection. I would have gotten the same set. The hard way is to actually take everything from the universe and see if it's in both. So pull out your inkwell and say, is that in this set? No, it's not. Okay. How about a mouse? Is there a mouse in this set? No. Okay. But if you start with one set and just go through those elements, you can find the intersection. So Venn diagram, there's your set A, there's your set B. This is the intersection. So two sets A and B are said to be disjoint. If their intersection is the empty set. So what are the elements that are in common between these two sets? There are no elements in common between these two because 1, 2, and 3, none of those are found over here, and that's everything that's in the first set. So the intersection of these sets is the empty set. So these two sets are disjoint from each other. And an interesting side note here, when I took the union, I had 2 things here, 2 things here. The union had 2 plus 2, 4 things. Here I had 2 things and 2 things. I took the union, I ended up with fewer than 4 things. Because if there's something in the overlap, it's only going to show up in the union once. So in all cases, the cardinality of A union B will be less than or equal to cardinality of A plus cardinality of B. This is assuming A and B are finite. So if these are finite, the cardinality is just a number, so we can define addition and less than or equal to and so on. So the number of things in the union is less than or equal to the sum of the number of things in each set. But we can be more precise than that. So this is something I'm going to call the law of addition subtraction. I don't think it's a real law. But if we take two sets A and B and we look at their union, it's going to be no bigger than the number of things in here plus the number of things in here, but it might be smaller. How much smaller? Well, basically anything that appears in both sets is only going to get counted once in the union. So it turns out this is actually the case. The number of things in the union is equal to the sum of the number of things in each set minus the number of things in the overlap. And this is a cool fact. And there's one homework question that I ask you to think about. And when you're thinking about it, think about this property. All right, so Venn diagram, disjoint sets. Those are examples of disjoint sets where they have nothing in common. All right, subtraction. And there's two ways that we write subtraction in set theory. One is to use a minus sign. The other is to use a backslash. So A backslash B. And both of these mean A minus B. And it's not minus like arithmetic. It really means A take away B. It means start with this set and throw away anything that you find in B. So it's choosing a subset of A. And we can write this formally as the set of all elements in A such that A is not an element of B. So examples help with this. So suppose A is 1, 2, 3, 4, 5, B is 3, 5, 10, 12. A take away B, or A minus B, would be anything that's in A but not in B. So it's a subset of A. Okay, will it contain the number 1? 1 is contained in A, it's not contained in B, so this is going to contain the number 1. What about the number 2? 2 is in A, it's not in B, it's going to contain a 2. What about the number 3? 3 is in A, but it's also in B, right? We want the things in A that are not in B. Since 3 is in A but also in B, it's not in A take away B. What about 4? 4 is contained in A, not contained in B, so 4 is in there. What about 5? 5 is contained in A, but it's also contained in B, so it's not in A minus B. And that's it. Those are the only things in A, and we've thrown away the things that were in B. Do we care that there's a 10 and a 12 in B? Nope. Has no effect on the answer. So when you're trying to do a subtraction, the easiest way, I think, is to start with the elements in A, and then just cross out anything that you find in B. And what you're left with, 1, 2, 4, that's your answer. So if U is the universe of all sets, if we start with the universe and we take away some set B, we're looking for every possible element that's not a member of B. And we have a special name for this. which is the complement of B. And we sometimes write this as B with a bar on top. The book writes this as B with a little C on the top. So if you see this in the text, it means the complement of B. You may see it as B with a quotation mark. I don't think we see that in the text, and I probably won't use that. I'll usually stick to B with a bar on top. Or I might use the words the complement of B, like on a test. But I think if I saw a single quote, I would interpret that as a complement also. A take away B is sometimes called the complement of B in A. But the more common use of complement is the complement of B in the universe of all possible things, which we just call the complement of B. So if this is A and this is B, this little piece here is A with B thrown away. And if this is a set B, all this stuff outside here, that's the complement of B. Complement of an infinite set is exactly the same, so this is not restricted to finite sets. So let S equal 1, 3, 5, 7, 9 equals positive odd integers. And let N equal 1, 2, 3, 4, 5 equals all positive integers. So if I had N take away S, what do I end up with? Any positive integer that is not odd. So this is going to be 2, 4, 6, 8, which is positive even integers. So in this case, the complement of an infinite set inside another infinite set is itself infinite. But that's not always going to be the case. We could take the complement of the prime numbers in the set of positive integers, and what do we get? We get the set of composite numbers. We'll spend a week playing with primes later. So there's lots of ways we can grapple with infinities that are not as kind of slippery as some other ways. All right. So let's talk about set operations. Sorry, set identities. We've done operations, ways to combine sets. Well, sooner or later, once you're combining things and making new things from old things, someone starts trying to generalize and come up with properties of applying these operations. So we're led to these set identities. And we'll go through some of this, and then we'll switch to the homework, and then we'll be good for the day. So again, let A, B, and C be sets. And I think they could be infinite sets or finite sets. So what do you think I get if I take A and I union it with the empty set? Where A is just some arbitrary set.
We just come out with A.
Just going to come out with A. Because what's the union? It's everything that's either in A or in the empty set. Well, there's nothing in the empty set, so I'm just going to end up with exactly A. What about if I take A and I intersect it with the empty set?
You get an empty set?
Going to get an empty set. Right? Because the intersection is a set of all things that are in both sets. Well, even if I have something that's in A, it's not going to be in the empty set. So there's nothing I'm going to find that's in both of these, so that's the empty set. How about if I take A and I union it with the entire universe of all possible elements? What do I end up with?
U.
End up with the universe U. What about A intersected with the universe? Yeah, coming up in chat, that's just A. Because again, the intersection is everything that's in A and also in the universe. Well, if it's in A, it's in the universe. So this is just going to be good old A. What about A union with A?
A.
Good old A. And A intersected with A is also going to be A. What about if I take the complement of A?
A.
Good old A. Because this is saying, you know, give me everything that is not in A. And this is saying, give me everything that's not in the set of everything that's not in A. And if you can work through all the double negatives, that ends up just being A. Someone's getting the vibes. This is commutative. Because there's really nothing in these definitions of union and intersection where the order of these things make any difference. Right? In some sense, the reason this is commutative is because this OR statement is commutative. So A union B is the same as B union A. Same with intersections. And we also have associativity. So we can do multiple unions or intersections in whatever order we want. Because, you know, this is everything that's in B or C. And this says everything that's in B or C or in A. Which is just everything that's in A or B or C, which is everything that's in A or B or C. And the same for intersections. We have distribution. Where if we take B intersect C and we union that with A, it's the same thing as A union B intersected with A union C. That takes a little more work to show, but let's look at that on a Venn diagram and just see if it's plausible. So here's A, here's B, here's C. So B intersect C is this stuff right here. Right, that's B intersect C, and if we union that with A, we get all of this stuff. So that's A union the quantity B intersect C. This right-hand side, A union B intersect A union C. Well, there's A, there's B, there's C. So A union B is all of this stuff. And A union C is all of this stuff. And if you look at the overlap for those, it's going to be all of this stuff and all of this stuff. So if you do this with like colored pencils, it's much more fun. But it turns out distribution works. So let's bring the vibes home. These are also true identities. The complement of A union B is the intersection of A complement with B complement. And the complement of A intersect B is the union of A complement and B complement. And who remembers what this is called? Good old De Morgan's. And we are going to bump into De Morgan's theorem several times this course. In set theory and counting and in all kinds of different contexts. And this is the first one. This is Engineering 250. Right? If you're getting that vibe, it's more than just a vibe. This is Boolean algebra. And it's Boolean algebra because the way we define a union is based on an or, and the way we define an intersection is based on an and. And if you take these definitions and you write them out to see what something like, you know, A union B complement is, right, where a complement is something that's not in there, if you write it out and you rearrange the words, you will find that using De Morgan's theorem lets you take this and show that it's equivalent to that. So this is good old Boolean algebra. Engineering 250, we're never going to get away from it. And all of these, you know, are analogs. If we replace the empty set with 0, the universal set with 1, ors replace the unions, ands replace the intersections. These are just theorems from, you know, beginning of Engineering 250, end of 120. And you can go through the examples from 250, the page of theorems, and for every statement in Boolean algebra, you can translate it to a statement in set theory. And, you know, so you can do things like A union complement of A equals the universal set, A intersect the complement of A equals the empty set. Well, this was just, you know, X and X bar equals false, X equals true, X or X bar equals false. You never escape 250. It's foundational. It will be there the rest of our lives. All right, so let's take a few minutes and run through the homework. And Friday, I want to talk about what are called membership tables, which will turn out to be truth tables. But we'll talk about membership tables, we'll play around with unions and intersections, we'll talk a little bit about functions, and then we'll start talking about infinities, just for fun. The cool thing about being in school is, like, you know, so someone just said in chat they took 250 a while ago, and they're not sure how much they remember of it. But the underlying concepts usually stick around in our brains. and you encounter them again in another course, and they come back with a vengeance, you know. And the fourth or fifth time you encounter them, they start to solidify. So how many people love KVL, KCL from ECS120, right? I had a PhD in electrical engineering. I never knew KVL, KCL till I came to Clark and started teaching it. But when you get into physics, right, you'll revisit KVL, KCL, and it will have been a few years, and chances are you're going to know more about it than you think. And you'll be ahead of people in physics who haven't had ECS 120. So yeah, these things keep building on each other, and that's really part of the fun of learning things, I think. All right, so let's take a quick look at the homework that I've posted, and I think you have enough to do, certainly to make a really good attempt on most of the homework. So let's bring this up. So I'd like you to write this up and turn it in as a PDF by 12:30, beginning of class on Monday. And let's go through what these questions are asking. So these are all from chapter 1, okay? So questions from parts 1.1, 1.2, and 1.3. So 1.1, I want you to look at questions 2 and 4. So questions are at the end of each chapter. And by the way, I usually give you even questions. The odd questions, almost all of them have worked out answers in the back of the text. So if you want more practice doing these questions, just go after the odd numbered questions and work through them, and then you can find answers in the back. All right, so question 2, we've got set builder notation here. So list the elements in each of the following sets. The set of 1 over n, where n is 3, 4, 5, or 6. So this set contains 4 elements, right? It's the set of every possible thing of the form 1 over n, where n is a member of this set. Okay, here we want the set of all elements alpha contained in the alphabet. This can be, you know, the English alphabet, where A precedes F. This one is funny. The set of all negative k, where k is in the set of positive integers. And if you don't know what something like, you know, this funny looking p is, look earlier in the chapter and it will tell you what it is. So I think p is the positive integers. So for any k in this set, negative k should be a member of this set you're going to write down for C. The set of all n squared, where n is this, and so on and so forth. So list all the elements. Well, if there's an infinite number of elements, don't write them all out, but do something to, you know, show me some of the elements and then tell me what the entire set looks like. So yes, 2a would start with 1/3 exactly. All right, question 4 is going in the opposite notation. What would be the correct notation for writing it down in homework? So if there's a small number of elements, you can just write curly brackets and list the elements separated by commas. Okay, but don't just list a bunch of numbers side by side, right? Show me a set. Or you could use words, right? The set containing, you know, all the negative numbers or something like that, all the negative integers. Whatever you think is going to describe it. Question 4, we flip this around. I'm showing you a set and you're asked to write a description of it using this kind of set builder notation. So don't just say the set of all x such that x is 1, 2, 3, 4, 5, 6, or 7, right? Try to come up with a different way to describe the elements in this set, or in this set, or in this set. This is like so much of the work in this course. It's puzzles, right? It's trying to find interesting ways to, you know, for example, describe these 5 numbers without actually listing them. So think about them, see if there's a pattern you could leverage, right? All right, so that's questions 2 and 4. Section 1.2, which is set operations, I'm going to ask you to do questions 4, 6, and 8. So question 4 is Give examples to illustrate the following facts. And I'm giving you some guidance in the homework here. When I say give examples, what it means is pick two specific sets, A and B. Either show me the contents or describe exactly what they are. And then show exactly what the contents would be for the left and right sides. For example, to show this first piece, if A is a subset of B and B is a subset of C, then A is a subset of C. You should list three sets, A, B, C. Show me what the elements are. And then convince me that A is a subset of B. And then convince me that B is a subset of C. And then convince me that A is a subset of C. How do you convince me? Well, basically just state it, right? But pick sets where it's clear from looking at it with whatever description you add that this is true and this is true, and then show me that that's true. Now, these are not proofs. We're not proving that if this is true and that's true, then this thing is true. We're just demonstrating a particular example. Show me an example where A minus B is different from B minus A. So this is all about working with these set operations with some sample sets that you get to pick and using those to demonstrate some property. Okay, so that's question 4. Question 6 deals with universal, with infinite sets and operations, which we started to touch on earlier. So suppose use an infinite universe. A and B are infinite subsets. Answer the following questions. So is the complement of A finite? Is A union B... Sorry?
This is section 1.2, yes.
This is section 1.2, right. So think about these and answer them and try to put down some explanation, right? Most of these homework questions are really about helping you get more familiar with some of these concepts. So think about these, write out some explanation. Question 8 I'll let you read and think about. It's a potentially really long problem to do, but think about it in terms of that law of addition subtraction that I mentioned. Okay, and we can talk more about it later on. And then one question from section 1.3 on Cartesian products, and you're being given a pair of sets and answer a couple of questions about the Cartesian product of those. Not proofs yet. We will get to proofs in chapter 3, but we'll develop proofs very carefully, and we'll go through a lot of information on how to do proofs, and that'll be a good thing when we get there. All right, that's it for the homework. That's it for our time. Well, we have 4 minutes left, but that's enough for our time. So that was the homework discussion, but that was actually a few minutes ago. Cool. Go ahead and start digging into the homework. We'll talk about any questions you have on it on Friday. And then Friday we'll finish up talking about set operations, and then we'll go on and we'll have some fun talking about cardinality of sets and such. So the textbook, if you go to Canvas, you can get to the textbook right here. And it's a free PDF. All right, have a good afternoon, everybody. I will see you next time.